Hello everybody, my name is Pedro Mariano and I'm going to present a work entitled Pollution Prediction Model using data collected by a mobile sensor network. This work is being developed in the context of the Polis project, which is funded by the Portuguese Foundation for Science and Technology. The goal of this project is to develop a network of mobile sensors that are going to be deployed in Lisbon city buses. Their aim is to complement data collection by static stations by providing a more detailed map of air pollution. We also plan to develop a set of tools to bring pollution awareness to citizens. We have already developed a mobile app to view real-time data and a health route planning web service. We also plan developing a pollution prediction model, which is the subject of this talk. As the sensors are not yet deployed in city buses, so we don't have any data collected, we instead used data from the OpenSense project, which was a project developed by EPFL, ETH Zurich, and other Swiss institutions. This data was collected from mobile sensors deployed on the trams of the city of Zurich. We are interested in doing pollution prediction based on geographical properties such as road area and vegetation surface area. Computing these geographical properties takes time, so instead of using the raw coordinates of each data sample, we instead computed a grid with length 2 meters, and for each grid cell with a data sample, we computed its geographical properties. Other attributes that were used to build a pollution model were minute of day, day of week, and week of year. In this slide, we can see the histograms of the data collected by the OpenSense project and that we use in our models. Number of particles, particle diameter, and lung deposit surface area. This last data is responsible for pulmonary diseases. If you look at the histograms, you can see that there are more samples with low values with a prevalence of 2 orders of magnitude. Now, regarding the model that we used, we selected decision trees because it is very fast to explore parameters, and also their learning algorithm is very fast. It's log n on the number of samples. There are, however, limitations on the models that can learn with decision trees. The parameters that we explored were the maximum depth of the tree and the number of samples threshold used when expanding the tree. If the numbers of samples associated with the tree node is above this threshold, then the algorithm will pick an attribute in order to make a split of the samples. We also consider other models, but their learning algorithm is dominated by the number of samples, which in the case of OpenSense project is in the order of 36 million. For instance, the backpropagation algorithm used to train neural networks varies linearly with the number of samples, but also with other parameters that describe the network architecture, such as the number of layers, K is equation, and the number of neurons represented by the parameters M, H, and O. K-nearest neighbors is another method that has good results in terms of prediction, but also depends on linearly on the number of samples. Gaussian process, it's also another method with good results, but in this case it has a cubic time and space constraints. Now, for the results of the perimeter exploration, as I said, we varied tree depth and the number of samples threshold. The tree depth is shown on the horizontal axis of these 3 graphs. And we varied from 10 layers up to no limit. And regarding the number of samples threshold, you use 0.1%, 0.05% of all the entire data set, but also we also set 1 sample as a threshold to create a new node. The vertical axis in both plots show the regression prediction error of the model. The learning parameters that produce the best decision trees were the ones where there were no restrictions on the depth of the tree, and where the algorithm kept expanding, creating nodes until just one single sample remained. As such, these were the nodes that were used on the ablation experiments. Another note is that if you look at the regression prediction error, and if you compare with the histograms, we can see that the error is 1% of the range of entire collected sensor values, which also is indicative of how well the models are predicting the pollution values. Now, in the ablation experiments, we wanted to see which attribute was more important in terms of the regression prediction error. If removing an attribute would decrease the performance of the learning model. And we opted to remove one or two attributes. On the horizontal axis, we are showing a time attribute that was dropped. In our case, we wouldn't use in the learning algorithm either the minute of day, day of week, or the week of year. And alongside each panel, we also dropped one of the geographical attributes. For instance, on the middle panel, we dropped the vegetation, so we just use only roads. And on the rightmost panel, we only use the vegetation, meaning we dropped the road attribute. And we also repeated the experiments using all the attributes, namely on the leftmost panel and on the leftmost column. Again, we are showing on a vertical axis the regression prediction error. Now, if we examine the error for all the collected sensor data, we can say that if we drop a time attribute, then the error increases only for the particle diameter and for the LDC sensor data. This means that the time is important in terms of predicting the pollution value. Now, regarding the geographical attributes, you see that if you only use the vegetation attribute, we can see that the regression prediction error decreases. So it seems that the algorithm is better in focusing, just only needs vegetation to predict the pollution value. So, wrapping up, the regression prediction error is 1% of the measured sensor values. The ablation experiment showed that time attribute is important for predicting pollution, and that the vegetation attribute alone decreases regression prediction error, hinting that it is an important geographical attribute. As for future work, we plan on using less data in order to use other regression models. Some ideas are sampling the data and using grid cells with enough measurements. And thank you for your attention.